Characteristics of N-channel JFET. Welcome to D Creations Resources. Now we have seen what a JFET is, we have seen its construction and also its operation, the concept of depletion region and the concept of pinch off voltage, etc. Now let's talk about the characteristics of JFET. Now there are two kinds of characteristics. One is the output or drain characteristic and other is the transfer characteristics. So the output or drain characteristics basically gives relationship between the drain current and drain to source voltage, that means ID and VDS, at different values of gate to source voltage, that means VGS. So here you are going to fix VGS, see the behavior of ID with respect to VDS, then take next value of VGS, again see the same behavior and so on. We begin by adjusting the gate to source voltage to 0 volt, then increase the drain to source voltage in small suitable steps and record the corresponding values of drain current at each step. So if this graph is plotted, we can see that we can divide basically this into several regions. Now before we divide it, we need to understand that whatever we did for VGS is equal to 0, we need to repeat the same procedure for different values of VGS. VGS is minus 1 volt, minus 2 volt, etc. unless and until the current becomes 0. Now the characteristics can be divided into different regions. 4 regions you can say. First is the ohmic region. So in this region, the drain current increases linearly with the increase in drain to source voltage. So basically it's obeying Ohm's law. So there is linear increase in the drain current when the N-type semiconductor bar is acting like a simple resistor. So when voltage is increased, current is increasing simultaneously. Then there is next part in which the drain current increases at the reverse square law rate with the increase in drain to source voltage. It means that drain current increases slowly as compared to that in ohmic region. It's because of the fact that with the increase in drain to source voltage, the drain current increases. This in turn increases the reverse bias voltage across the gate source junction. As a result of this, the depletion region grows in size, thereby reducing the effective width of the channel. At the drain to source voltage corresponding to point that you can note on the characteristic, the channel width is reduced to a minimum value and it's called pinch off. The drain to source voltage at which the channel pinch off occurs is basically the pinch off voltage. We've already talked about it. And the next region is pinch off region. Now here, this is also called saturation region or constant current region, because in this region the drain current remains constant at its maximum value, that means IDSS. The drain current in the pinch off region depends upon the gate to source voltage, and of course there is a relation that ID is equal to IDSS into bracket 1 minus VGS upon VP whole square. It's called Shockley's equation. And pinch off region is the normal operating region of JFET if it is to be used as an amplifier. The last region is breakdown region. Now here the drain current increases rapidly as the drain to source voltage is also increased. This happens because of the breakdown of gate to source junction due to avalanche effect. The drain to source voltage corresponding to this point is basically called a breakdown voltage. Now if you go to another value of VGS, or if you want to see what is the effect of increasing gate to source voltage on the drain characteristics, basically there are two things that are going to happen. One is the value of pinch off voltage is reached at a smaller value of drain current as compared to the value VGS is equal to 0. And secondly, the value of drain to source voltage VDS is decreased as compared to that when VGS is equal to 0. So if you want to study the effect of gate to source voltage on drain characteristics, you will see that similar curves are obtained, but the saturation value of the current is much lower as compared to that at VGS is equal to 0. And you can understand it from the fact that the reverse bias voltage across the gate source junction of JFET is the sum of gate to source voltage and drain to source voltage. Thus, for a fixed value of VDS, the increased value of VGS will increase the reverse bias across the junction. For example, consider the case when VGS is minus 1 volt. When that is applied between the gate and source of JFET, then the gate to source junction becomes reverse biased even when the drain current is 0. This causes the depletion region to be formed within the channel. As the voltage VDS is increased above 0, the drain current increases. This produces voltage drop across channel resistance, which in turn produces reverse bias voltage across the gate source junction. The amount of reverse bias voltage required to be produced by drain current would obviously be decreased by 1 volt. In other words, a smaller voltage drop along the channel, that is smaller than when VGS was 0. So this smaller voltage drop will increase the depletion region to the point where they will pinch off the drain current. So as a result, the pinch off voltage is reached at a lower value of the drain current than that when VGS is equal to 0. Also, the fact that the increased value of gate to source voltage keeps adding to the reverse bias at the junction produced by the drain current. We can see the second effect, that is the value of VDS is decreased as compared to when VGS is equal to 0. Now, the next characteristics is transfer characteristics. So this is also called transconductance curve, and here we obtain the relationship between drain current and gate to source voltage VGS for a constant value of drain to source voltage, that is VDS. The transfer characteristics can be obtained where first of all we adjust the drain to source voltage to some suitable value and increase the gate to source voltage in suitable steps. And then we record the corresponding values of drain current at each step. Now, if a graph is plotted with gate to source voltage along the horizontal axis and drain current along the vertical axis, we get a curve where we can see that the upper end of the curve is shown by the drain current value equal to IDSS, while the lower end is indicated by a voltage equal to VGS off or VP. So these are the two kinds of main characteristics, drain characteristics and transfer characteristics. Now next we will be seeing the differences or the comparison of field effect transistor and bipolar junction transistor. That means comparison of FET and BJT.